Okay, so today's video is about comparing three or more means. We've already looked at the difference between two means, where we checked to see if the difference between two means was equal to 0 or less than 0 or greater than 0. Well, this is a little bit different. I could take my three means, if I had three means to compare. I could test group 1 and 2, group 2 and 3, and group 1 and 3, and do three different paired tests. But as the number of groups that I'd be comparing goes up, then the number of two paired tests that I would need to run would go up too. And that could lead to, that gets risky, because the more of those I do, the greater my chances of having a type 1 error is. So what we really need is is one test that compares all the means to see if any of them are different, significantly different from the others. The Anova test is just the test for that. Their requirements for an Anova F test are that the samples are randomly selected in an independent manner from the K is the number of treatment populations. The populations must be normally distributed, and the populations need to have the same variance. All right. There's a little bit, let me go back a minute. There's a little bit you need to know about the Anova test. First of all, the distribution, it follows a Fisher distribution, Fisher F distribution, and the critical value, or the test statistic, is called the F statistic. So we're looking at the Fisher distribution, which looks different from a normal. It's characterized by two numbers. You know how the T distribution, depending on the degrees of freedom, depends on the shape of the distribution. Well, the Fisher distribution depends on two different degrees of freedom. So the first degree of freedom divided by the second degree of freedom. And the first degree of freedom is the number of groups or categories minus 1. And then the second degree of freedom in the denominator is our sample size, or the number, minus the number of groups. Okay, so we'll talk a little bit about that, more about that in a minute. I think it'll be easier to understand if we have an actual example. So we have a researcher wants to determine if there's a difference in mean shear bond strength among 4 different treatment groups for repairs of chipped porcelain veneer. God, I hate when that happens. Is there a difference in the mean bond strength of the different treatments? So we're looking at porcelain teeth, you know, like crowns and caps. And we're looking at repairs made to those, porcelain repairs. And we're looking to see if there's a difference in the strength of the repairs. So our significance level, our alpha level, is 0.05. And I'm going to draw a picture for all of you people who need a visual. I don't know what that distribution actually looks like, but alpha is 0.05. And for this test, we're not actually going to do, for the notes, we're not actually going to do any calculations. I'll wait and do a full example with the calculator in class. You're just going to need to be able to read this printout here. Okay? So you'll notice that we need our F alpha. We don't have our critical value. And if you look up here, this column here with DF, degrees of freedom, is an important column. Okay, so this tells me that I have 19 degrees of freedom total, that comes from the number, or sample size, n minus 1. That gives me 19. So that tells me that my sample size was 20. So that's my total, n equals 20, because n minus 1 equals 19. So that means n equals 20. Okay, so if I go up here, I have 4 different groups. I have Cojet, Sillastor, Samara, and Ceramic. Those are my 4 companies who make porcelain veneers, and I'm checking to see if there's a difference between any of them in their strength. So I have 4 groups minus 1, and then I have 20 is a number of samples. That means I must have had 5 samples of each, minus the number of groups, which would be 4. So that gives me 3 over 16. Now I need to look this alpha up in my book, because I don't have that distribution in my calculator. So that is on page A18, and that table runs all the way through, nope, actually it starts on A16 and runs through to A19. So it's a 3-page, 4-page table. 4 pages of tables. So in my table, I don't have a picture of it, I have degrees of freedom up here in the top in the numerator. So I'm going to look for, and then I have numbers 1, 2, 3, 4, and so on. On the side, I have degrees of freedom in the denominator. And I have 1, and then I have, with that 1, I have a list of area in my right tail. So I have like 0.1, 0.05, 0.025, and so on. I have like 5 for each one. And then I have 1 for 2 with these alpha values. So that's the degrees. This here is my degrees in my denominator. Okay, so I have 3 in my numerator. I have to go over to this line. I have 16 in my denominator. I'm going to go to page A18, and you'll notice that when you do that, I have degrees of freedom in the denominator down this column. On that page starts at 9 up here, then goes to 10, then 12, then 15. And then it starts going by 5s and for a while, and then 50s. So you're going to pick the one that's closest to 16, and that is 15. So you go to 15, and then you find the area next to that of 0.05, and then you go across the table and down the table, and you will find that it is about 3.29. Okay, so I already have this information printed out, probably from Minitab. And if you look up here, there's my test statistic, and here's my p-value. So you can compare this now to the critical value. That is in my critical range for sure, because it's greater than 3.29. And also my p-value is 0.002. So that's also another indication that it's in the critical region. So F is greater than F alpha, and P is less than alpha. That means that we would reject our null hypothesis, which I forgot to write. Null hypothesis is that our mean 1 is equal to mean 2, is equal to mean 3, is equal to mean 4, and my alternate hypothesis is that at least one mean is different. and that's always the null and alternative hypothesis. At least one mean is different. So we would reject the null hypothesis in this case because our test statistic is in the critical region, and that would say that at least one of these ceramic treatments has a different mean than the others. Okay, let's go ahead and do another example. This time, how about we start with properly and make our null and alternative hypothesis. So, a stock analyst wondered whether the mean rate of return of financial, energy, and utility stocks differed over the past 5 years. He obtained a simple random sample of 8 companies from each of the 3 sectors and obtained the 5-year rates of return. At the significance level of 1%, is there evidence to conclude that the mean rates of return are different? So we have financial, energy, and utilities. We have 3 means that we're comparing. So our null hypothesis is that mean 1 equals mean 2 equals mean 3. And our alternate hypothesis is that at least one mean is different. All right, and we need to calculate our degrees of freedom now. First of all, we need n, and since n minus 1 is 23, then that means that n is 24. And k is 3. We have 3 means that we're comparing, 3 groups. So the degrees of freedom in the numerator are 3 minus 1, and in the denominator they're 24 minus 3. Remember, it's k minus 1 over n minus k. So that's going to be 2 over 21. So then I'm going to go to my table, and on page A18 is where I'm going to find the closest to 21 degrees in my denominator, and I'm going to have to go down to 20 because that is the closest that I have. Let's draw a picture here. My alpha is 1%, so that's 0.01, and F alpha, I'm going to go down to the 21, and then I'm going, so that'll be down this way. I have to find 20, and then I have to find the 0.01 that is in 20, and then I have to go over and cross-reference that with the 2 degrees of freedom on the top. And when I do that, it looks like alpha is not alpha, but F alpha is about 5.85. Okay, so now I can go over to my printout here, and my F statistic is 2.08. That's in this region, not my critical region, and P is 15%, which is greater than alpha. So since F is less than F alpha and P is greater than alpha, we would fail to reject our null hypothesis. It looks like there's no significant difference between the means of financial, energy, and utility stocks. Okay, third example. Researcher Francisco Fuentes and his colleagues want to determine the most effective diet for reducing LDL cholesterol. He looked at a saturated fat diet, Mediterranean diet, and the National Cholesterol Education Project. That is the NCEP1 diet. Heck, I don't care about cholesterol. I want to know how to lose some weight. Where's the study on that? All right, back to work. After 28 days on each diet, mean cholesterol levels were tested. Are the mean LDL cholesterol levels different at a 0.05 level of significance? So we have the saturated fat diet, the Mediterranean diet, and the National Cholesterol Education Project diet. So that means that we have 3 groups. And if we look down here, n minus 1 is 41. That means that n is 42. All right, let's set up our null hypothesis. We're going to say that mean 1 equals mean 2 equals mean 3. And our alternate hypothesis is that at least one mean is different. You can tell I'm getting tired of writing that out because I started writing cursive. Okay, and then if I draw a picture, and we're looking at a 5% significance level, we need F alpha. So the closest, let's do our degrees of freedom. K minus 1 over n minus k is going to be 2 over 39. So looking down at my table on page A18, I have 25 and I have 50. I don't have a 39, but 39 is 11 away from 50 and 14 away from 25. So I'm going to go with 50 degrees of freedom. And I'm going to look, so I'm going down the table until I find the 50. And I'm going to look at 0.05. And then I'm going to go across to the 2 degrees and cross-reference that and find the number that goes with that. So 50 degrees at a 0.05 and 2 degrees of freedom on the top is going to give me about 3.18. Okay, so my F value is 5.43. That's bigger. That's on this side. And P is 0.008. So F is greater than alpha, F alpha, sorry, and P is less than alpha. We're going to reject our null hypothesis. That means that at least one diet's mean cholesterol levels are different than the others, at least one. All right, that's all I have for you today. I will see you in class